In this screencast, we're going to solve the equation of motion that we've already developed for this simple single spring, single mass system. And we're going to use this information to develop our understanding on what's called simple harmonic motion and how this system moves. So far, to solve an equation of motion, we've only used separation of variables, and this is where we separate the variables to each side of the equal sign and we integrate. Now this is a legitimate method, but it requires you to eventually use, in this case, a trigonometric substitution. This is all the things that you learned in calculus 2 for solving integrals. And in the book, in Kasdan and Paley, they demonstrate this. And so I encourage you to take a look at that, and you'll see that the integral that you would eventually have to contend with. And it's really not that pretty, and you have to have tables. But what we're going to draw on to solve this equation are the concepts that you learned in your differential equations course. And in there, you developed a new set of tools that you apply to differential equations. And so the first step that we're going to do is we're going to make this easier by changing the coordinates. So we've already defined a coordinate of x, but in our differential equation, we're referencing this to a constant, which is x naught. So we're going to change our coordinates, and now we're defining the quantity x minus x naught as the coordinate z. And so all that's doing is saying that instead of referencing our fixed point within the inertial reference frame I, we're now referencing the resting position of where the mass lies, and only considering this displacement z. And so the substitutions that we'll make are that x is equal to z plus x naught, just by rearranging this equation. When we take the first time derivative, we get z dot plus 0, because this is a constant, and the time derivative of a constant is 0. And then x double dot, when we make that substitution, will be equal to z double dot. And so when we make those substitutions, our equation of motion is z double dot, the acceleration of our new coordinate, is equal to negative k over m, so that's our spring constant and our scaled by the mass, multiplied by only z. And we'll rewrite this, because we want to solve this differential equation, we'll rewrite this as z double dot plus k over m times z is equal to 0. Now as you take a look at this differential equation, you should recognize some distinguishing features. First off, it's second order. All of our differential equations in this course are second order. It's also linear, and it's also, when you look at the right hand side, it's homogeneous. And then in addition to that, we have constant coefficients. We have a coefficient of 1 and then a coefficient of k over m. And this is great news, because linear, homogeneous, constant coefficient differential equations have a well-defined solution process that's based on the characteristic equation. And the characteristic equation is a quadratic polynomial set equal to 0, where lambda squared is our second time derivative, lambda 1 is our first time derivative, and lambda the 0, of course, is equal to 1. And when we look at our coefficients for our differential equation that we're solving, then we get the characteristic equation of lambda squared plus k over m is equal to 0. Now recall how this characteristic equation works is that when we solve for the roots of this equation, then that tells us how the system responds. And in our situation, our roots are complex conjugates. You can obtain this solution by plugging into the quadratic formula, and for our complex conjugates that we have, we get a real portion of 0, and then our imaginary coefficient is the square root of k over m. Now, when we see complex roots, this tells us that our solution is oscillating. And so now we have to assume, when we're solving differential equations, we assume a solution form. And the general form for this system is that we have an exponential decay in which we use the real portion as our time constant, and then we have our oscillating portion, which is governed by the complex part. And in this case, we need to put in both the cosine and the sine because they're linearly independent, and then we've included this square root of k over m as the coefficient on our time variable. And then we have these undetermined coefficients a and b. And so first thing you can see is that because our real portion is equal to 0, that there is no exponential decay in this system. And so this portion is equal to 1. Now let's look at one more portion of this to make our notation simpler and give us more intuition on this system. So take a look at square root of k over m. Now this term is a little bit cumbersome and doesn't really give us much intuition on the system yet. But let's take a look at what the units are within this expression. Recall that we define the units of our spring constant k with the units of kilograms per second squared, and then mass has the units of kilograms. And when we take the square root of this, these two cancel, and we get the units of 1 over seconds. And this is a frequency. And this tells us how the system will oscillate, the frequency at which it will oscillate when it's unforced. And remember, an unforced system is our homogeneous. This is when we have our zero on the right-hand side of the equation. And we have a special name for this frequency. It's called the natural frequency. And we designate it by omega naught. And it's simply equal to the square root of k over m. So what we see is that the natural frequency of the system increases if we increase our spring constant, which is the stiffness of the spring according to Hooke's law. And then when we change our mass, if we increase our mass, it will decrease the natural frequency. And so now we take these elements and plug them into our general solution. And our only unknowns now are these coefficients a and coefficient b, which we can determine by applying the boundary conditions. We're solving a second-order differential equation, so we need to take our assumed solution for the position, z, and then differentiate this twice to be able to get z dot and then z double dot. We get these two expressions by taking the time derivative of the position and then taking the time derivative one more time of the speed to be able to get the acceleration. And if we've assumed correctly on our general form, then we should be able to plug these into our equation of motion, substituting z double dot on the left-hand side, and then substituting z into the right-hand side, and demonstrate that they're equivalent. So now we'll determine the actual expressions for the state equations by solving for the coefficients a and b that appear in both the position and the speed equations. Now we'll do this by applying our boundary conditions. And that's just saying that we have at initial time is equal to 0, that we have an initial displacement that we'll call z0, and an initial speed, which is z dot 0. So when we substitute these boundary conditions into our position equation, we have that z is equal to our initial position. We have a, our coefficient, cosine of 0 because it's at time 0, plus b multiplied times sine 0. The cosine of 0 is equal to 1, and the sine of 0 is equal to 0. So that means we can solve this equation for the coefficient a, and we get that a is equal to our initial position. Then when we apply our boundary conditions to the first time derivative of z, we've substituted our initial speed on the left-hand side at time 0, and then inserted our coefficient for a. At time 0 is sine 0, and then we have b, omega naught, cosine 0. Now we know that sine 0 is equal to 0, and cosine 0 is equal to 1. And so we can solve for our undetermined coefficient b, and that's equal to the initial speed divided by the natural frequency. So now let's convert back to our original coordinates, and that means that our coefficient a is going to be equal to our initial position minus the resting length of the spring, and then our coefficient b will be equal to x dot, our initial speed, divided by the natural frequency. And so we substitute all of this into our equations, and then we get the final solution for our state as seen here, in which we have a function for our position that's based on the resting length of the spring and the initial position, and then also the initial speed of the system. and also incorporates the natural frequency. And then we get a similar expression, which is also oscillatory, which is the first time derivative. And if we solve this system and we have no initial speed, but we do have an initial position, so we're essentially pulling that mass and then letting it go, which would be an initial position condition, then it's going to oscillate continuously between the initial position and then the opposite side of the resting length. So initial position and then the negative initial position around the resting length at a particular frequency. And that frequency is defined by its period. So if this is the period t, and we all know that t is equal to 1 divided by f, and this is when f is equal to the natural frequency, and our natural frequency is typically in radians per second, so we need to divide that and get that into hertz by dividing by 2 pi. And so the reason why this solution is important is because the form that we started out with, which is x double dot is equal to some constant, I'll just do a big C, multiplied times the position, is that this form of the differential equation shows up very frequently in dynamics. And what we're able to do is we're able to take large, more complex systems and then simplify them. We'll reduce them to a much more simple form that looks something like this, and will always have this form of the solution. And this means that if you can recognize this form of the differential equation and then know how the state evolves over time, you can quickly gain insight into how the system behaves.